One of the first questions I remember asking, which is, what else is out there? And I would look out my childhood window at the little patch of the sky, and I just remember wondering what they were and what else was out there. And I remember having this feeling almost of restlessness.
The Big Bang is one of the most fascinating topics you can bring up when conversing with scientists and astronomers. This is because the theory talks about how the whole universe started in the first place. However, the event that led to the Big Bang is one thing that is being argued among scientists today. For this reason, the James Webb Telescope was called in to make some findings about the Big Bang. The JWST certainly found something, but it wasn't something the scientists had prepared their minds for. What did the James Webb Telescope discover, and in what way would it affect the Big Bang Theory? Join us as we explore the James Webb Telescope's terrifying discovery before the Big Bang. It all began when an astronomer cited a discovery made by the James Webb Telescope. Astronomer Rowan Naidu was at home with his girlfriend when he discovered the galaxy that almost broke cosmology. He was inspecting some of the images the James Webb Telescope sent earlier when one of the images caught his attention. The telescope had identified an object that Naidu recognized as mysteriously huge. It dates back to the Big Bang era, making it older than any galaxy we once knew in science. It was a shocking discovery for him as he called his girlfriend to observe the most distant starlight too. He was praised for this discovery by his team, and then they got to work. A few days later, Naidu and his team published a paper on the discovered galaxy called Glass Z13. It was a discovery that had the whole world of science come to a standstill, as no one expected such a discovery to be made by the James Webb Telescope. The James Webb Telescope made this ancient galaxy discovery just a few weeks after it went into operation. It was a huge achievement because if such a discovery could be made a few weeks into the telescope's launch, what next would it discover? The JWST, the most powerful telescope currently in use by scientists and astronomers, and the Hubble Space Telescope's successor, was built to make us understand our universe better, and it's already achieving that feat. The telescope is 1.5 million kilometers away from earthly interference, where it orbits the Sun. It is equipped with a sunshade about the size of a tennis court, with huge segmented mirrors and very sensitive tools designed to detect details about the universe and its entirety that have never been explored. This period detected by the JWST is known as the scarcely probed era, which explains how the very first stars and galaxies were formed. The events surrounding this process seem partially uncovered by scientists, as the entire process depends on exotic physics. But now that such a discovery has been made about the Big Bang era with the James Webb Telescope, cosmologists would be able to dig deeper into more phenomena that have been left unsolved. This involves either confirming the validity of their best consensus models or revealing gaps in understanding that could bring about new discoveries. This ranges from uncertain influences of dark matter and dark energy to the faintly understood feedback between starlight, gas, and dust. Such observations were supposed to take time, as initial projections had estimated that the first galaxies were going to be so small that the JWST might have a hard time finding some of them during its investigations. But the $10 billion powerful telescope proved the predictions wrong and sent astronomers and cosmologists back to work as soon as it sent back its first images of the distant universe. Upon receiving the images, astronomers such as Naidu began to find several galaxies within the images that outshined all predictions about size, age, and luminosity. It was an irregular period that almost made scientists freak out, as Naidu wasn't the only one that made these discoveries. Several research groups also made their discoveries from the images sent back by the JWST. It nearly turned into a field of competition as news of other record-breaking galaxies kept coming from different research groups. It was something scientists never expected. Shortly after the JWST found these galaxies, theorists and observers began to check them out, looking to explain the phenomena. They began to wonder if the bevy of anomalously big and bright early galaxies was illusory, or could it have been flaws in the telescope's initial observations? But if these discoveries were genuine, could they be analyzed by standard cosmological models? Theorists also thought, could these discoveries be the first hints that the universe is more strange and complex than even our boldest theories had supposed? One thing this discovery made by the JWST puts at stake is our understanding of how the universe we know emerged from prehistoric chaos. This means that the JWST's early discoveries could be a factor that would rewrite the opening chapters of cosmic history, which does include not only distant epochs and faraway galaxies, but also human existence here in our familiar Milky Way. A senior advisor for science and exploration at the European Space Agency, Mark Makorian, commented on the discoveries made by the JWST. He stated, "You build these machines not to confirm the paradigm, but to break it. You just don't know how it will break." The JWST's observations of early galaxies have been billions of years in the making, but honestly, they only trace back to the Space Telescope Science Institute, STSCI, in 1985. At this time, the JWST's predecessor, the Hubble Space Telescope, was still 5 years away from launching on a space shuttle. But Garth Illingworth, the then deputy director of the STSCI, was surprised when his boss, Director Riccardo Giacconi, who passed away in 2018, asked him a weird question. Giacconi asked his deputy about what would happen next after the Hubble Space Telescope made its discoveries. Illingworth was shocked at the question as he protested there was still much work to do on the Hubble Space Telescope, but Giacconi didn't budge. After that conversation, Illingworth put together a team and they began to draw up concept ideas for what they referred to as the Next Generation Space Telescope, NGST, later renamed the James Webb Telescope after former NASA administrator James Edwin Webb. And the need for the JWST telescope was made pressing in December 1995 when astronomers pointed the Hubble Space Telescope at a seemingly empty patch of sky for 10 days in a row. Several experts predicted the Hubble observation for 10 days would yield nothing much, and at its best would reveal some dim galaxies. But the results from the Hubble Space Telescope shocked them. This image, known as the Hubble Deep Field, showed that the empty spot it was pointed to contained thousands of galaxies dating back to 12 billion years into the 13.8 billion year history of our universe. Illingworth, now an astrophysicist at the University of California, Santa Cruz, recalled the discovery, saying there were galaxies everywhere. With that image, the Hubble field showed that the early universe was more crowded and exciting than most scientists had expected. It became a lost but now found treasure to astronomers and scientists who took the time to look properly. Despite how mind-blowing Hubble's deep field was, astronomers and scientists still wanted more, and that led to the birth of the James Webb Telescope. After over 2 decades of hard work and innovation at the cost of $10 billion, the James Webb Telescope was launched on December 26, 2021. Its journey started and it reached its deep space destination a month later. At this stage, the JWST had to go through powerful testing to ensure its optimal performance. This testing continued till July 2022, when it was ready to start its first year of science observations, which scientists titled Cycle 1. Parts of these early observations were dedicated to high-impact programs across several disciplines from which the data would be publicized immediately. 2 of these disciplines, SEERS, the Cosmic Evolution Early Release Science Survey, and GLASS, the Grissom Lens Amplified Survey from Space, independently spent dozens of hours looking for galaxies in the early universe by staring at separate small portions of the sky. Scientists didn't expect much from the JWST. At most, they expected a clearer version of the Hubble Deep Field, with the detection of extremely distant galaxies to pop up after a few cycles of data from multiple programs. However, the James Webb Telescope immediately showed its worth, as the first sets of observations made brought about the galaxies in the images spotted by Naidu and other astronomers in research groups. The influx of scientific papers about the JWST's initial observations was no accident, because as the first data began streaming down, astronomers and theorists started to write scientific papers and theories about their discoveries. But some scientists looked at the idea of having numerous scientific papers over the first sets of observations with concern. Klaus Pontoppidan, JWST's project scientist at STSCI, expressed his concerns, saying people in research groups might have rushed things a little bit. He gave his reasons, saying that early collaboration issues with JWST, for example, may have affected some results. Nathan Adams at the University of Manchester in England and his colleagues found dramatic changes could occur, with one galaxy at a redshift of 20.4 recalibrated to a redshift of just 0.7. However, these issues are not likely to eradicate JWST's high redshift galaxies, given their total number. Because of the number of galaxies seen and reports made by the scientists who discovered them, the odds of all scientific reports being wrong are small. As a result, scientists are looking to conduct follow-up observations with the James Webb Telescope. As a matter of fact, several research groups are sending proposals requesting more time to use the James Webb Telescope for space observations. The majority of these proposals seek to scrutinize high redshift galaxy candidates. Regardless, more programs are set to kick off in the hunt for distant galaxies. One such program is the Cosmos Webb project. The mission is expected to increase the known populations of early galaxies by observing a wide sector of the sky for hundreds of hours, maybe a whole month or more. Scientists believe that thousands of galaxies out there are yet to be detected, and this mission would find them. There are several theories trying to explain how the universe started. They include the steady-state universe, which denies the possibility of a beginning and end for the universe, but says the universe is continuously expanding while still maintaining the same overall density. In other words, a steady-state universe is forever identical, but continually growing bigger in scale. In this model, galaxies, planets, and other forms of matter are locked in continual recreation. Since the density remains the same, old astronomical objects become unobservable as new creations take their place. Another competing theory is the bouncing cosmology or Big Bounce model, which says the universe shrinks to a minimum volume and then bounces back into a subsequent expansion. There is no shortage of theories of how the universe began, so there is the plasma or electric universe model. Plasma is the word given to the fourth state of matter, that is solid, liquid, gas, and plasma. A plasma is a gas that is so hot that some or all of its constituent atoms are split up into electrons and ions, which can move independently of each other. In plasma or electric universe theory, plasma takes up an integral role in cosmological events and the fundamental order of the universe, proposing electric currents that flow along plasma filaments capable of shaping and powering galaxies. These currents stream into stars, powering them like fluorescent bulbs and inducing the births of planets. There are more theories about how the universe began, but the most popular one is the Big Bang, and you can thank the popular TV show The Big Bang Theory for bringing it further to the masses. It is also the most widely accepted in the scientific community. This theory was born of the observation that other galaxies are moving away from our own at great speed in all directions, as if they had all been propelled by an ancient explosive force. A Belgian priest named Georges Lemaitre was the first to suggest the Big Bang Theory in the 1920s, when he theorized that the universe began from a single primordial atom. The idea received significant boost from Edwin Hubble's observations that galaxies are speeding away from us in all directions, and from the 1960s discovery of cosmic microwave radiation, interpreted as echoes of the Big Bang by Arno Penzias and Robert Wilson. Further work has helped clarify the Big Bang's tempo. Here is how the Big Bang went. In the first 10 raised to the power of minus 43 seconds of its existence, the universe was very compact, less than a million billion billionth the size of a single atom. It is thought that at such an incomprehensibly dense, energetic state, the four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, were forged into a single force. Still, current theories haven't yet figured out how a single unified force would work. To pull this off, we'd need to know how gravity works on the subatomic scale, but currently we don't. By the time the universe was a billionth of a second old, the universe had cooled down enough for the four fundamental forces to separate from one another. The universe's fundamental particles also formed. It was still so hot that these particles hadn't yet assembled into many of the subatomic particles we have today, such as the proton. As the universe kept expanding, this piping hot primordial soup, known as the quark-gluon plasma, continued to cool. Some particle colliders, such as CERN's Large Hadron Collider, are powerful enough to recreate the quark-gluon plasma. The radiation was so intense in the early days of the universe that colliding photons could form pairs of particles made of matter and antimatter, which is like regular matter in every way, except with the opposite electrical charge. It is thought that the early universe contained equal amounts of matter and antimatter, but as the universe cooled, photons no longer packed enough punch to make matter-antimatter pairs. So, like an extreme game of musical chairs, many particles of matter and antimatter paired off and annihilated one another. Some excess matter survived, and it's now the stuff that people, planets, and galaxies are made of. Our existence is a clear sign that the laws of nature treat matter and antimatter slightly different. Researchers have experimentally observed this rule imbalance called CP violation in action. Physicists are still trying to figure out exactly how matter won out in the early universe. While scientists talk with confidence about what happened after the Big Bang, what exactly took place before the Big Bang? We will soon get to that after answering these two interesting questions related to the Big Bang. Where did the Big Bang take place? When a stick of dynamite explodes, the detonation occurs in one place, and shrapnel flies into the void. However, in the Big Bang there was no center and no pre-existing void, so it didn't happen at any location per se. Space itself popped into existence and began expanding everywhere at once. Some astronomy books compare the universe to a rising cake, with raisins representing galaxies. As the cake grows, raisins recede from each other with no center of expansion, just like the Big Bang. But, of course, a cake has an edge, unlike the universe, which may go on forever. In the real sense, no analogy can perfectly capture the Big Bang. Also, was the Big Bang a one-off? Well, at the beginning of the Big Bang, there was the inflationary vacuum. When it doubled its volume, it doubled its energy. When it tripled its volume, it tripled its energy. If banknotes were like this and you pulled apart a stack, ever more would appear. Physicists call inflation the ultimate free lunch. The inflationary vacuum expanded ever faster, but it was a quantum thing, and quantum things are fundamentally unpredictable. Randomly, all over the inflationary vacuum, parts of it decayed into an ordinary, everyday vacuum. The Big Bang is the story of how we got here and how the universe got started. And while a lot has been said about the Big Bang, what exactly happened before it? What existed in what form and for how long? This is one of the reasons scientists are excited about the JWST, because it's the only tool that can allow us to see billions of years into the past, enough to have a peep behind the Big Bang. But what exactly is singularity? Singularity, also known as the Planck epoch or Planck era, was the earliest known period of the universe. At this time, all matter was condensed on a single point of infinite density and extreme heat. During this period, it is believed that the quantum effects of gravity dominated physical interactions and that no other physical forces were of equal strength to gravitation. This Planck period of time extends from point 0 to approximately 10 raised to the power of negative 43 seconds, which can only be measured in Planck time. The extreme heat and density of matter rendered the state of the universe highly unstable. It thus began to expand and cool, leading to the manifestation of the fundamental forces of physics. From approximately 10 raised to the power of negative 43 seconds to 10 raised to the power of negative 36, the universe began to cross transition temperatures. It is here that the fundamental forces that govern the universe are believed to have started separating from each other. The first step in this was the force of gravitation separating from gauge forces, which account for strong and weak nuclear forces, and electromagnetism. Then from 10 raised to the power of negative 36 to 10 raised to the power of negative 32 seconds after the Big Bang, the temperature of the universe was low enough at 1028 Kelvin that the forces of electromagnetism or strong force and weak nuclear forces or weak interaction were able to separate as well, forming two distinct forces. This was followed by the inflation epoch, lasting from 10 raised to the power of negative 32 seconds in Planck time to an unknown point. Here, the universe was filled homogeneously with a high energy density, and the incredibly high temperatures and pressure gave rise to rapid expansion and cooling. This began at 10 raised to the power of negative 37 seconds, where the phase transition that caused the separation of forces also led to a period where the universe grew exponentially. It was also at this point in time that baryogenesis occurred, which refers to a hypothetical event where temperatures were so high that the random motions of particles occurred at relativistic speeds. As a result of this, particle-antiparticle pairs of all kinds were being continuously created and destroyed in collisions, which is believed to have led to the predominance of matter over antimatter in the present universe. After inflation stopped, the universe consisted of a quark-gluon plasma, as well as all other elementary particles. From this point onward, the universe began to cool and matter coalesced and formed. Next was the cooling epoch, where the universe decreased in density and temperature, and the energy of each particle began to decline. Phase transitions continued until the fundamental forces of physics and elementary particles changed into their present form. Since particle energies would have dropped to values that particle physics experiments can obtain, this period onward is subject to less speculation. This was then followed by the structure epoch, which expands over billions of years down to our day. The slightly denser regions of the almost uniformly distributed matter of the universe began to become gravitationally attracted to each other. They therefore grew even denser, forming gas clouds, stars, galaxies, and the other astronomical structures that we regularly observe today. It was during this time that the modern universe began to take shape. This consists of visible matter distributed in structures of various sizes, ranging from stars and planets to galaxies, galaxy clusters, and superclusters, where matter is concentrated, that are separated by enormous gulfs containing few galaxies. But you may be asking, where did the Big Bang take place? That is a fair question, because if you hear an explosion outside, you may be fairly accurate in pinpointing the spot where it occurred. So can we travel to the spot in the universe where the Big Bang took place? Perhaps scientists can find a huge crater somewhere in the universe that corresponds to the ground zero of the event. The fact is that there is no such spot anywhere, because there is no exact spot where the Big Bang happened. The Big Bang actually happened everywhere, if that makes sense. Never mind that the term Big Bang conjures up explosions or detonation. Meanwhile, even though the Big Bang theory is widely accepted, it is not without its critics. There are some unresolved issues when scientists try to explain the beginning of the universe with the Big Bang theory. The first is the horizon problem. You see, there are portions of the universe that are visible to us but invisible to each other. Horizon problem says that different regions of the universe have not yet contacted each other due to the great distances between them, even though they have the same temperatures and other physical properties. We know that CMBR is found to be homogeneous everywhere, so how is this possible? The observed isotropy of the CMB is the problem in this regard, because we believe that information is not supposed to travel faster than light. However, the resolution of this apparent inconsistency is offered by inflationary theory, in which a homogeneous and isotropic scalar energy field dominates the universe at some very early period. According to Heisenberg, there were quantum thermal fluctuations during the inflationary phase, which would be magnified to cosmic scale. These fluctuations functions as the seeds of all current structure in the universe. Inflation predicts that the primordial fluctuations are nearly scale invariant and Gaussian, which has been accurately confirmed by the measurement of the CMBR. The instant before inflation began, the universe was only about 10 raised to the power of minus 24 centimeters in diameter. All matter and energy were in close and uniform contact within the briefest instant. The universe then expanded exponentially by a factor of about 10 raised to the power of 50, sending once intimately connected matter and energy to the farthest reaches of the universe. The information contained in the pre-inflationary universe didn't have to travel the speed of light, it traveled at the speed of inflation. Another problem with the Big Bang theory is known as the flatness problem. The thing is, according to Einstein's field equations of general relativity, the structure of space-time is affected by the presence of matter and energy on small scales, making space appear flat. This is just like how the surface of the Earth seems flat if one is looking at a small area, but on a large scale, space becomes bent by the gravitational effect of matter. The amount of bending or curvature of the universe depends on the density. What about the events that preceded the Big Bang? Humans are curious and are not satisfied with knowing only what happened post-Big Bang. We want to know what occurred before the event that started it all. This is not an easy thing to do, however. For instance, the cosmic dark ages prevent us from traveling back in time to see what happened during the Big Bang. The cosmic dark ages were a time when the universe was enveloped by a fog of neutral hydrogen that trapped the light of the first stars and galaxies. The fog didn't lift until 1 billion years after the Big Bang, when the neutral hydrogen had been reionized and once again split apart. Because light couldn't escape its surroundings during the Dark Ages, it couldn't journey outward through the universe to hit our detectors here on Earth nearly 13 billion years later. Even before that, there wasn't much light before the first stars formed because aside from hydrogen atoms, most of the universe was made up of dark matter which doesn't emit light. So how do we leap over these dark periods and go right past the Big Bang to see what happened then? Where did all the initial energy come from? This is basically like trying to answer the question of who were you before you were born? This is where Stephen Hawking stepped in. Hawking regularly blew our minds with his theories on what happened and what's to come in our universe. For instance, he explained how we humans might have about 100 years left on Earth. He also predicted the Earth would become a nice ball of fire within about 600 years. Anyway, we are talking about the less doomsday-esque scenario of what happened before the Big Bang. Here is how the brilliant physicist approached it. There ought to be something very special about the boundary conditions of the universe, and what can be more special than the condition that there is no boundary? Stay with us, it gets more interesting from here. The no-boundary proposal, which Hawking and his frequent collaborator James Hartle fully formulated in a 1983 paper, envisions the cosmos having the shape of a shuttlecock. Just as a shuttlecock has a diameter of 0 at its bottommost point and gradually widens on the way up, the universe, according to the no-boundary proposal, smoothly expanded from a point of 0 size. Hartle and Hawking derived a formula describing the whole shuttlecock, the so-called wave function of the universe that encompasses the entire past, present and future at once. This renders moot all contemplation of seeds of creation, a creator, or any transition from a time before. Hartle and Hawking's proposal radically reconceptualized time. Each moment in the universe becomes a cross-section of the shuttlecock. While we perceive the universe as expanding and evolving from one moment to the next, time really consists of correlations between the universe's size in each cross-section and other properties, particularly its entropy or disorder. Entropy increases from the cork to the feathers, aiming an emergent arrow of time. Near the shuttlecock's rounded-off bottom, though, the correlations are less reliable. Time ceases to exist and is replaced by pure space. As Hartle explained it recently, we didn't have birds in the very early universe, we have birds later on. We didn't have time in the early universe, we have time later on. Hawking himself wrote about time. Events before the Big Bang are simply not defined because there's no way one could measure what happened at them. Since events before the Big Bang have no observational consequences, one may as well cut them out of the theory and say that time began at the Big Bang. On a Neil deGrasse Tyson show, Hawking also said, "Nothing was around. The Euclidean space-time is a closed surface without end, like the surface of the Earth," he said. One can regard imaginary and real time as beginning at the South Pole, which is a smooth point of space-time where the normal laws of physics hold. There is nothing south of the South Pole, so there was nothing around before the Big Bang. Hawking and Hartle considered the possibility that the universe began as pure space rather than dynamical space-time, leading them to the shuttlecock geometry. They defined the no-boundary wave function describing such a universe using an approach invented by Hawking's hero, the physicist Richard Feynman. In the 1940s, Feynman devised a scheme for calculating the most likely outcomes of quantum mechanical events. To predict, say, the most probable results of a particle collision, Feynman found that you could sum up all possible paths that the colliding particles could take, weighting straightforward paths more than convoluted ones in the sum. Calculating this path integral gives you the wave function, a probability distribution indicating the different possible states of the particles after the collision. In the final years of his life, to better understand the wave function more generally, Hawking and his collaborators started applying holography, a new approach that treats space-time as a hologram. Hawking sought a holographic description of a shuttlecock-shaped universe in which the geometry of the entire past would project off of the present. That effort is continuing in Hawking's absence. For the past year, Neil Turok and his Perimeter Institute colleagues Latham Boyle and Kieran Finn have been developing a new cosmological model with much in common with the new boundary proposal. But instead of one shuttlecock, it envisions two arranged cork to cork in a sort of hourglass figure with time flowing in both directions. While the model is not yet developed enough to make predictions, Its charm lies in the way its lobes realize CPT symmetry, a seemingly fundamental mirror in nature that simultaneously reflects matter and antimatter, left and right and forward and backward in time. One disadvantage is that the universe's mirror image lobes meet at a singularity, a pinch in space-time that requires the unknown quantum theory of gravity to understand. Boyle-Finn and Turok take a stab at the singularity, but such an attempt is inherently speculative. This explanation of the pre-Big Bang period by Hawking has been fascinating and inspiring physicists for years now. They find it stunningly beautiful and provocative. It was basically the first guess at the quantum description of the cosmos or the wave function of the universe. Soon, an entire field, quantum cosmology, sprang up as researchers devised alternative ideas about how the universe could have come from nothing, analyzed the theory's various predictions and ways to test them, and interpreted their philosophical meaning. The no-boundary wave function was, in some ways, the simplest possible proposal for that. Or perhaps there was something else before the Big Bang that is worth pondering. One idea is that the Big Bang isn't the beginning of time, but rather that it was a moment of symmetry. In this idea, prior to the Big Bang, there was another universe identical to this one, but with entropy increasing toward the past instead of toward the future. Increasing entropy, or increasing disorder in a system, is essentially the arrow of time, Carroll said. So in this mirror universe, time would run opposite to time in the modern universe, and our universe would be in the past. Proponents of this theory also suggest that other properties of the universe would be flip-flopped in this mirror universe. For example, physicist David Sloan wrote in the University of Oxford Science blog that asymmetries in molecules and ions, called chiralities, would be in opposite orientations to what they are in our universe. At any rate, another theory holds that the Big Bang wasn't really the beginning of everything, but rather a moment in time when the universe switched from a period of contraction to a period of expansion. This notion suggests that there could be infinite Big Bangs as the universe expands, contracts, and expands again. So to summarize, the Big Bang theory is the leading explanation for how the universe began, and in its most simple form, it says that the universe as we know it started with an infinitely hot and dense single point that inflated and stretched, initially at unimaginable speeds and then at a relatively measurable rate over the next 13.8 billion years to the still expanding cosmos we see today. So far, the Big Bang is our best guess about the origins of our universe, but now it seems that these new images from the JWST are making some scientists doubt the credibility of this theory. The Big Bang theory has been defended for multiple decades as an unquestionable truth by most cosmological theorists, but the new data from the JWST is making ones like Alison Kirkpatrick panic. She is an astronomer at the University of Kansas in Lawrence, and according to her, the latest revelations have made her question whether everything she's done in the field is wrong. The incredibly small, smooth, old, and surprisingly numerous galaxies are completely incompatible with the Big Bang hypothesis, in the opinion of a few scientists. The Big Bang proposes that the universe is expanding and a strange optical illusion must exist in outer space. Galaxies and other objects in the expanding space do not continue to look smaller with the increasing distance. Beyond a certain point, they start getting bigger, as their light is supposed to have left them when they were close to us. But the images of the JWST show them getting smaller and smaller. Even the galaxies with much greater luminosity and mass than our own Milky Way appear 2 to 3 times smaller in these images. In other words, the galaxies the JWST is showing us are the same size as the galaxies near us, indicating that the universe isn't expanding and that redshift isn't proportional to distance. The newer galaxies in the images have a redshift that is 2 to 3 times greater. This strongly contradicts the theory of an expanding universe, in the opinion of Eric Lerner and Ricardo Scarpa, but aligns with their prediction that we are part of a non-expanding universe. They had previously published results based on Hubble Space Telescope images that showed galaxies have a redshift all the way up to 5 that match the expectations of non-expanding ordinary space. They were confident that the James Webb would only confirm their hypothesis. Big Bang theorists had expected to see badly mangled galaxies scrambled by multiple collisions and mergers. However, the JWST images actually showed overwhelmingly smooth disks and neat spiral forms, just like we see in today's galaxies. The data in the Panic article shows that there were around 10 times more smooth spiral galaxies than predicted, and this challenges our ideas about mergers being a very common process. According to Lerner and Scarpa, this data utterly destroys the merger theory. The Big Bang theory implies that the most distant galaxies in the James Webb images are seen as they were about 400 to 500 million years after the origin of our universe. But some of the galaxies have shown stellar populations that are at least 1 billion years old. Now, according to the Big Bang theory, nothing could have originated prior to it, so the authors of the Panic article believe that the existence of these galaxies is proof that the Big Bang didn't occur. And just as there must be no galaxies older than the Big Bang, so theorists expected that as the JWST looked out further in space and time, the galaxies would become fewer and eventually there would be none left, signifying a dark age in the cosmos. But a paper yet to be published demonstrates that galaxies as huge as the Milky Way are common even a few 100 million years after the hypothesized Big Bang. From the Big Bang standpoint, the distant galaxies are supposed to be intrinsically smaller. One galaxy noted in the papers is GHZ2, and it is far more luminous than the Milky Way and yet is calculated to be just 300 light-years in radius. This is 150 times smaller than the Milky Way. And the JWST images aren't the only reason the Big Bang theory may be considered wrong according to Lerner. He believes that right now the Big Bang makes 16 wrong predictions and only one that is correct. Its prediction of helium is off by a factor of 2. The prediction for the abundance of lithium is off by a factor of 20. And besides the absence of larger and more distant optical illusions, there is also the existence of large-scale structures too big to have formed in the time since the Big Bang. Most cosmologists and astronomers have stated that there's an explanation for every doubt Lerner and Scarpa's article has raised. The Big Bang is definitely not dead, and the recent observations of the JWST haven't disproven the theory. These observations have revealed some unexpected and strange things about the universe, but that's all. The Big Bang is centered around 2 facts. First, that more distant galaxies have a higher redshift than closer ones, and second, that the universe is filled with a cosmic background of microwave radiation. These constitute 2 of the 3 pillars of data supporting the Big Bang theory, the third one being the relative abundance of elements in the early universe. But these are just the foundation of the model. In past years, scientists have expanded on these to create the standard model of cosmology, also called the LCDM model. Everything from acceleration of cosmic expansion to the clustering of galaxies support this model. The Tolman test predicts that if the universe was non-expanding and static, the surface brightness of all the galaxies would be the same regardless of the distance, which isn't the case as evident by the JWST images. The distant galaxies have a dimmer surface brightness than the closer ones in these images. It is a common misconception that redshift proves that galaxies are speeding away. They aren't in reality. Distant galaxies aren't speeding through space. In fact, space itself is expanding and thereby putting greater distance between us. This subtle difference emphasizes that the galactic redshift is a result of cosmic expansion and not relative motion. Experts aren't denying that what the James Webb Space Telescope found doesn't entirely align with their predictions, but astronomers were hoping to find this sort of puzzling data. They believe that is the reason why so much was invested in building the James Webb Space Telescope in the first place, and they understand that the data collected by this magnificent telescope doesn't tell us that the Big Bang model is wrong, but some of their assumptions about it could be.